simplest way in multidimensional calculus is the primitive curves. Okay, so it's just the two regular functions that you've seen before. Okay, so all right, and so why do we care? In addition to any kind of motion as to model. So when there is a horizontal vertical motion separately, that's fine, but that's either it is too simple when we split dimensions and or they're too complex. They're too complex because any kind of physics and say planetary motion requires forces. Forces require acceleration. Acceleration requires second derivatives. So we're not doing second derivatives here. Okay, so then fortunately there are a bunch of applications outside of kind of physics, but rather more say social possible. Although the physical model is still the same, is this flow? The flow, each arrow indicates the direction of the flow at that location, how fast in direction and the magnitude of the velocity of the flow at that location, and then you're supposed to solve how you solve it. You're supposed to draw somehow these curves that each of which parameter curves, so that at every point each tangent line is like okay. So the challenge is pretty much the same as in dimension one. Okay, so we did the modeling. Okay, we did the analysis, that is the qualitative analysis. We came to the conclusion that we cannot separate the three options. Remember, so the arrows are there. We confirmed that's solid knowledge, but we cannot tell which one, how the effect on without solving this. So we cannot tell for sure that it will come back exactly to the same spot. Okay, so you cannot naturally you cannot expect for modeling to expect that to happen. It comes back with an error always. So even if it was supposed to exactly to come back, with the error it won't. Okay, so that's actually what happens as we started to discover later on at the end, is that it is a periodic. Okay, but modeling cannot discover periodic behavior for you, because how do you exactly hit the same? It's an approximate curve. How will it exactly hit this spot to create this repetitive procedure? So it's either one or the other, or the third, but we cannot tell. Okay. If you are, it's like you know, about the universe that's supposed to be flat. Anybody knows that theory? You know, the curved universe. Anyone? No, the universe is curved. The relativity relies on this part of the theory that everything is happening because the universe is curved, and they try to measure it, is it curved or not, and every time they get zero. Doesn't mean that it is zero. No, because it's a process. So, which the worst case scenario, because if it's zero, then you don't know. It could be zero, could be positive, could be negative. Same story. You don't know. And so our modeling produced the picture in the middle, and but you know that we'll see why it produced the picture on the right and what's on the left. The picture in the middle, not on the left. So the true picture is on the right. The modeling produced the picture in the middle, and the left one we did not appear. And we can figure out why. So the algebra, analytic method of solving the problem is turns out that we can separate the variables, but not like it was before t and x. We're separating x and y. Okay, x and y are separated by solving by treating the fractions as the derivative as fractions. Remember? Okay, so and then solving for dt, and we have two equations, and therefore we each dt. You eliminate dt, end up with a single equation at the bottom there, with no t. Okay, so then we speak of differential force with respect to x and y. Okay, that happens to be equal to each other, and that now we exactly the same place as before with separation of variables. Now we integrate. Okay, so integrate with respect to variable that is present there. It's really not even. So that may be worth a point. Integrate over x or y. Well, There is no such thing as integrate X or Y. So if you were to integrate with over X or Y, that's the word that actually used, but it is a mistaken way of looking at this. If we had two functions equal to each other, the say y equal x squared, then you can integrate with respect to x. So integral y dx equal to integral x squared dx. So that's we're used to this. But the two functions equal to each other, the integrals also equal to each other. This makes perfect sense. But here we're not integrating with respect to y, we're integrating with respect to the variable that's already there. Okay, so that's the x is here. Okay, so in other words, we just add the values together, if that makes sense. On the x and the values on the y, this is because they are the same, they're supposed to add up to the same value. That's what integral sign stands for. It's things together, and it's because these are made of the same pieces. They taken together, they will also produce the exact same amount. So we end up with two antiderivatives. Naturally, that part doesn't change. So once we have written our integrals here with respect to dx and dy, we carry out the integration, logarithm will come up. I am using only one, as before, only one constant c. Okay, and then what we have here is a very the step that we are very happy to observe is that there is no differentiation left. Okay, so that's when we say that the differential equation has been integrated. Derivatives have been eliminated, even though the equation has not been truly solved, because the solution, remember the solution actually, the solution was, what is the meaning of solution? Solution is x of t, y of t. This is the parametric curve. That's the solution. That's what we're supposed to have, and we don't. Okay, and we won't. Okay, so well, we might, but how? So as you can see, when you look at it, there is no t in the first place. How do you get from here to there without t? And the answer is we really can't. Okay, so then what is the point? So what is so great about it, other than this appearance of the differentiation? What's the equation? What kind of equation is it? What does it give us? An equation? Well, alpha, beta, gamma, and delta are constants. Okay, let's say c is also constant. So let's fix everything. Then we have only two variables, x and y, and we have an equation. So what is that? What do we have? Potentially. Equation with respect to x and y, what I would talk about. Seen it a few times. An equation with respect to x and y. Can we plot it? Yeah. Okay, so what will we get? Graph. A graph specifically a curve. Probably doesn't have to be a curve, but it could be a curve. It's a relation. The relation, we've seen a bunch of those before. I don't know. You can go 2x plus 3y is equal to 7, or x squared plus y squared is equal to 4. This is a relation that kind of, or xy is equal to 3. We've seen all of these, not only elsewhere in this exact class. We've seen all of it. Straight line, circle, hyperbola, parabola, all of these are exactly that. So is it whether is or is it not solved for y in terms of x makes no difference. It's still a relation, and potentially, if everything is fine about it, it's a curve. So a curve on the, so if we can plot it, we have a curve on the xy plane. What's the significance of that plane? Oh, I'm sorry, of that line, of that curve.
So why can't be zero?
Well, x and y in simultaneous. Well, logarithm is undefined as zero in the first place, so no, they cannot be equal to. Yeah, so okay, so what you're pointing out, I think, is the limitation of this thing that and that is worthwhile mentioning, that x cannot be equal to 0 and y cannot be equal to 0. But fortunately, those two are remember the xy plane that we only cut the first quarter from it. quadrant rather, from it, and the rest is not important. The X and Y axes themselves are important, but they're trivial in the sense that, well, it means that either one population or the other population is zero, so we can handle what's left, the other population. Foxes without rabbits or rabbits without foxes, so we know how they're going to behave. The rabbits will do this and the foxes will do that. Okay, so what does this curve, that curve, have to do? That's the question with this solution right here. Solution that we don't know, but the idea is that we may be making a step in that direction.
Relates to two that previously postulated.
Yeah, you can say that. So technically, a solution is how X depends on T independently and Y depends on T once again independently. So we're not getting that, but we're getting something entirely different, seemingly dependence of X and Y on each other. Okay, but once you start thinking about the curve, you realize both of these are curves. So that's not a coincidence. Parametric curve, and this is also a curve. So even though the two different functions by nature, if you start plotting them, they might be the same. What's the difference? And the difference, let me try to describe that in the kind of a geometric language. This is the road, and this is the trim on that road. Okay. So the time when time is absent, what you're getting the road on which you have traveled. You left a trace behind you. Your tire tracks behind, and then but you don't. If somebody comes, they see the tire tracks, but they don't know when you were there. Okay, so you're leaving that trace behind without markings. So it's not as good. It's not as good as the solution, which is the same, but also a curve, but with markings. Remember, parametric curve. What is it? It is the same road. What's the strip is a road with time labels. Okay, remember that example of parametric curve when it is literally your trip for force doesn't matter, or on the road. Then what is how you plan your trip, or you write about it later. You not only provide the curve, the road or the path, but also mark where the location where you were at that time. At what time you were there. Okay, so that's the difference. So this thing will give us the road, but will not give us the trip. So which means that we don't know what's the difference. We don't know how fast we're moving. That once again, you see tire tracks, unless you're kind of some kind of tracker, you cannot tell how fast the car was moving. You cannot, once again, if you don't look carefully, you cannot even tell which way you're going. The car was going that way or this way. You have to actually read the tires. The tire tracks if you want to tell. So it's not as good. It's not as good, but it is surely will it gives us a lot of progress, because at least we're going to be able to tell us that is it periodic or not. If it's a curve, does it come back or not? That surely we will be able to tell. So it's called an implicit solution. Okay, so just as before, so we had those solutions. Remember, X and Y are related to each other, but not necessarily solved with respect to one, with respect to the other, one with respect to the other. So it's not as good, but it's better than the other. Okay, so in the first quadrant, the Lotka-Volterra equation satisfy this equation that we have. As you can see, a nicely separated X and Y's from each other. C, remember what C stands for. And what's the meaning of C? Is it, yes, a constant, but which one? I don't specify with that constant, so what does it tell me?
Just multiple.
Yes, a multiple, not multiple, really multiple. It's a family once again, just like we had before. We say it's a family, and we expect a picture to be very similar once again. It is a plane, or at least a quarter, filled with curves. That's for every C, there's a curve, and once again, they're the same story. We expect that the whole origin is filled with curves without intersecting. So that's what we expect. Okay, so T is absent. This is once again, this is this is the analysis now. The analysis is we take that function and this is the trick. How do we figure out what those curves look like? Oh, we create a function of two variables. Okay, so we take that function, extract C. Okay, so C will be the variable. Okay, and it's not variable, it will be what variables. Okay, we create a function of two variables at the bottom. See here, delta x minus gamma ln x minus alpha f y plus beta y. Those four parameters, remember? So, and then what do we know about this function? Okay, so as a function of the variables, the idea then is before we analyze the function is the idea is if we were to substitute our solution, which remains unknown, if we were to substitute that into this equation, what we're going to get is a constant. Okay. So once again, each t gives you a point xy of the xy plane. That xy plane is substituted in this function that we know now entirely, and that what it produces produces the z, but that z is constant. Okay, so that's the z. It happens to be must be constant. Okay, this is a function. Okay, we have a function that is unknown p, the known function g. We take a composition from t to xy, for xy to z, which creates a new numerical function. So generally speaking, you expect something like this. This is t, this is z, and then this is t, this is z, and then you may have something. Okay, but it turns out that is the case unless that function p is in fact a solution to our differential equation, in which case the function is not anything. It is very simple. It's a constant function. Okay, so that's what we're claiming is that it's not this, but rather this. Okay. So, okay, so it's a composition, the substitution of a parametric curve on the xy plane into the function defined by on the xy plane. So I'm not sure if you remember this picture of how you compose two functions. Well, once again, parametric curve on the plane. That's the very first picture. Okay, so once again, as you can see, we're moving for xy plane. It's a curve, but not only it's a curve, but also it is marked with labeled with time moments. Okay, the arrows also necessary to know which way we're going. Okay, so that's one function. Okay, the second function is the terrain. Okay, so the simplest example, if you can set aside the whole thing about predator prey and just think about the compositions here. So that's an important thing. And so then what is that we have here? We have two pieces of information. My trip that I have planned on a map. I have a map, and I put where I'm going to be at the location. The second what comes into play is the terrain map. That's the second picture, happens to be in plane, but that's just incidental. And then how do I know? Now the question I'm asking: how fast will I be climbing? So with this two pieces of information on the left, how fast am I will I be climbing? So my plan on the piece of paper and the terrain map, secondly, which exists entirely separate. So the first one is under my control, the second one is not. Okay, so to find out, I actually have to map out my actual trip. That trip is three-dimensional. I made a map on the 2 dimensions because that's what I had, but the actual trip will be happening in 3D. So what I'm doing here, I take my look at what's happens in the middle here. I draw my path on the underlying plane in the XY plane, and that picture over there is drawn on it. So that's the top picture here. Okay. So and then what I do is I lift this picture to the terrain in the vertical direction. See, you see here. So originally the curve on the left is plotted over there underneath, and then it's kind of a I can't think of a better word, but to be lifted to the surface that represents the terrain. That's the composition. Okay, and then it traces out, as you can see here, the path on the terrain. So that's the reality. That's the actual trip. Not the way I planned it, that would be the way I could, because all I had is a paper, but actually what is going to happen. So it not only includes the horizontal motion, but also the vertical. That's the reality, what is supposed to happen. And then fine, okay, so, and then what is our question really is the elevation. So which means that all I have to do is just to look at these elevations right there and how far I have to lift every of these points. And then the dependency is actually time from time to elevation. Okay, so the composition is once again as it has come up here. So time here, location, horizontal location. And this is vertical location. In other words, elevation. Okay, so we might be interested in eliminating the middleman and go straight to the dependence of elevation on time, which is on the right. As you can see, what happens here is actually going kind of a flat, more or less, and then going down. You can see that picture here, kind of flat and then down. Okay, so that's the composition of two functions, one of which is a perfect curve, the other one that follows is the function of the variables. We're exactly in that place, even though we're not talking about any actual motion, we're moving through our space of data, right? So data, kind of a space that we made up. X is the number of rabbits, Y the number of Y is the number of foxes, right? So but the composition in what we're trying to establish is the same. So we know what is that gamma is, or it would be G, not gamma. This is my G really. It's the terrain, and this is my solution. The solution that is unknown, okay? And we ask ourselves, what if we compose my solution with this function that doesn't have a special name, but nonetheless, it comes from our work that we've done. So this is my terrain. And what happens if we substitute one to the other? And the answer is we end up with a function of just numerical functions, time, something. Well, actually, this is the question: what is the meaning of Z? And I haven't thought about that, but that just occurred to me that that's a question, a fair question to ask. What is the meaning? This. So we know the meaning of X, we know the meaning of Y, and then we create this new function G, which is equal to X and Y. Okay, so but what is the meaning of it? Well, so it seems made up, frankly. But that's okay. So maybe there is some physical meaning. So you can look at the units. The units are kind of interesting here. Kind of weird combination of the number of rabbits and rabbits and then foxes. Well, okay, so just leave it as is. Anyway, and so then the point is really not that the composition is not so interesting. It is what the fact that it is a solution, which means that when we plug it into my function, I end up with a constant function, meaning constant elevation. So if the picture does not reflect that, because this is an entirely different story, but if it was, then our trip would be on a constant elevation. Okay, so is it clear what I'm talking about here? You can probably imagine a curve on that in the top left, drawn in such a way that when this procedure is carried out, the end result is constant. Okay. So can you imagine how would you go about getting that? So you're planning a trip, okay? So which is entirely in that terrain that you can go anywhere you want. You know you have the terrain map bottom left, okay? So now you are so lazy that you don't want to climb at all. No go down. You're going to want to stay on exactly the same elevation, which is, by the way, is already the problem is kind of solved. Hold on, where's here's the constant elevation. I don't want to go up or down. The terrain may be complicated. This one is simple. It could be complicated, but the question, my question might be, what if I don't want to climb? Can I just stay exactly on the same level throughout the trip? And it's possible to solve that problem. It is literally what is done every time you remember old fashioned maps. I'm not sure if you have you seen old fashioned maps without color? Anybody? How did they go about to, on a piece of paper, draw a map without using colors? Right?
Topography,
What?
topography,
Yes, topography. So how that?
circles.
Well, circles, curves, yeah, pretty much. So it will look like,
It
what?
created a curve that was projected onto map that was at a
Correct,
constant elevation.
correct. Yeah, so each curve is a curve of constant elevation. So it's literally called level curves. Okay, so nowadays they never do that anymore. They just give you a color right on it. So on your cell phone, just the color distinguishes the different elevations. But they used to do it in a cheap way. You draw a line and then you mark, say maybe this is 1,000 and this is 1,100 and 1,200 and so on. So that's how they would create a map, and which means it's very convenient. You know how much you're climbing. You also know which way to go. If you don't want to climb, just follow one of those curves, and then they don't have to be curves necessarily closed curves. It could be, this is, what does this look like? Possibly a hill on one or a mountain on one side, the mountain on the other side. It's a passage. So, yeah, so that's, they used to do it. So yeah, terrain, and then how do you present it in three-dimensional terrain in a two-dimensional paper? The answer is you kind of cut it in the horizontal fashion, producing curves, and then plot these curves and mark them with the elevation as a number. And then you end up with a bunch of circular curves, but also curves that are not circular. And in particular, if you do have two mountains next to each other, that's the spot. In the middle is where you would try to cross it. So high and high, and this is low and low. Okay. So anyway, so that's the problem we're solving is really very much typical for topography. Is finding the curves of constant elevation. Okay, so they call level curves, and that's roughly where we are right now. We have our terrain. That's the terrain, and what we would like to find is it is a curve that actually a curve, not just well, the curve itself would be the road. We want to more than just a curve. We want a permanent curve, but at the very least, we could try to figure out what those roads look like. So the roads of constant elevation. So I don't think it's a practical application of this thing is maybe, what's called a terrain, terrace agriculture, anyone? Know what this is? What is it?
It's reading. Playing a garden bed, but instead of just making straight rows, you follow.
Well, yeah, and it is a
Even
constant,
just level out a spot.
right?
Um,
And you see the picture, so a big hills going up, especially like Southeast Asia or something like that.
That's how they fix the dust bowl.
What?
How they fix the dust bowl.
Fix what?
The dust bowl,
Dust.
in the thirties where.
Really? Never heard this. You need it in rain. Not sure how did they do it?
Because when you just make the straight lines across the hills, it would create it would make it erode a lot faster, so like dust storms and everything. They learned that it's the terraced farming thing.
I'm not sure we're talking about the same thing, because, yeah, I think I understand what you're saying, so. They slow down the winds, and, yeah, so, but you can't really make on hills out of nothing to stop the hill, so they probably planted a lot of trees in order to prevent the erosion from the winds and those tornadoes, probably what I'm guessing. No, I'm thinking, so I'm not familiar, but what the picture that I have seen is once again, probably in Southeast Asia, and they frequently, they don't have flat areas a lot. Well, like here, and then what did they do? So they would cut in steps. They cut in steps on the mountain, but naturally each step is a horizontal one. Okay, so as if you make from a sloped terrain, you make it into a staircase. Okay, so and then each of these circles becomes a separate field. which looks exactly the same as the regular field because it's totally flat. Okay, so I think they still. Anyway, okay, so then we know what the relation between our solution that we're looking for and this surface is now clear. I hope, and then we can actually look at the let's plot it. Here's the plot of our function. Okay, so that function, I choose specific values for alpha, beta, gamma, and delta. So this is, by the way, not Euler or anything like that. It is literally a function with a specific formula. We have a specific formula, so that's not modeling. That's like literal, just collecting data in the form of an array, and then that array is plotted. This is done with Excel. Okay, so like I said, if you have a formula, we collect the data, big array of numbers on X, Y plane here somewhere, and then the number that is located in the cell is plotted as an elevation. And so that's a literally function of variables. And then Excel hides the fact that it's made of like bars. See, they could make bars, but instead they prefer to do it this way as just surface. So I'm smoothing it out. Okay, so let's take a look at it. What do you see? Anything you want to say about the surface? Once again, the meaning of the elevation is unclear, so it's not that what we're looking at. So how do we call this point? They would call this point right here. So right here. So go up from dimension 1 to dimension 2. So the terminology of calculus, you should be able to use here freely in a slightly different setup. The minimum, right? Minimum, it is the lowest point among all of these, as far as we can tell. Okay, and it seems to from that point, there's a growth in all directions. Okay, now do you remember what that point is? We saw this. We saw a special point. Remember, and remember what that point was. Special point. A point of, well, remember what X and Y stand for, stand for the number of rabbits, the number of foxes. So if I go down, what?
Equilibrium?
And that's right, we had an equilibrium point, remember? A point where the exact number of rabbits and exact number of foxes combine in such a way they eat each other in such a way that there is no growth or decline in either one of the populations. And that's exactly where the point is. Okay, the minimum point, and then that point, by the way, is also a curve. It's technically, the point is not a curve, but it is a solution curve. There's a stationary solution which is constant, right? So no matter what t is, it stays there. So that's another just a different way to describe equilibrium. And in the meantime, everything rotates around. So those level curves on our terrain is where our solutions travel. So the roads are the curves, okay, and our solutions are unknown at this time. Script that we take. So the time is not here. This is only X and Y and Z. So the time is not present, but we know if we were to set the population free and follow these dynamics, that it will be making these trips. So they do seem that they like to come here, but you can guess that they probably come back. Right, because it's a function, and then if you were to cut it like this, it definitely produces probably not definitely, but probably at this time, because we only have a model, a picture. It does appear to cut it in such a way that it cuts only the middle part of the surface, and then there are parts that are hiding. Okay, so there's a green part that's clearly a periodic solution, right? You can see here. or at least not periodic necessarily, but sort of surely repetitive. Okay, so it's supposed to come back, that's the green one. And now you can guess, this is an index as a guess, clearly there's a purple part that remains once you cut the green part out. Now, if you cut the purple part out, there seems to be the blue part left also, and so there's another circular or at least periodic or circular solution present there. And then the idea seems to be that no matter how high we keep cutting them here higher and higher and higher, the end result will be every time we end up with a curve that is what close. It's called a closed. Circles, ellipses that we have had, they all closed curves, and say parabola is not, and hyperbola is not. So does it run to infinity or not? And it appears that it's not possible, which suggests that indeed our model that we have has this kind of a benevolent result in a way that they will not, nobody will die out, and it will keep recovering, even though might be getting close to going into extinction, but will never will. It will be going up and down, and also there will be no explosion of the rabbit, so that they will eliminate, the ecosystem of the earth because there are too many of them. It cannot happen according to this picture. There is no runaway procedure that causes explosion. So it is a mild, even though it goes up and down, and there are some close calls. Over here somewhere, close calls possibly, but nonetheless close calls in circles. Period. That's what you want to see there. Okay, so any questions so far? Okay, some circular, others seem not circular, but they actually are. We cannot see the rest of them because it grows over here, especially that edge that faces us, right here, it grows so fast that we cannot, the Excel runs out of room, and yes, the numbers are too large. Okay, so okay, so match the graph with the vector field of the ODE given above, so that the one that I started with today. So the curves that we just saw, those level curves of our surface, we match them with this. Okay, so every time, and that's the idea, that our parametric curve, that once again unknown, but we do know that it will travel in a manner tangent to those level curves, because that's how we drive on a road. Your headlights rather always point in the tangent along the tangent to it. Okay, so if these were the roads, then and you were here, say, if you're here, then this will be your tangent. Okay, so that's the relation that we're thinking, and that's how we do two-dimensional differential equations, is a bunch of curves, parametric curves, and the tangent lines or vectors. That's why we need to study vectors next, and then their tangents to our curves. Not in the same way as a tangent a line, right? In calculus 1, this is more calculus 2, 3, and so we can't really do it without vectors. So a curve, which is just a curve, just two functions, but the derivative is trickier. It is made of vectors. It is a vector in every location. There's a vector, so it's a vector field. Okay, so I'll skip this. Okay, so let's do some algebra. Okay, so once again, getting to use some things from calculus 3. We have a function of two variables. What I did is I'm looking for a minimum point, and or confirm that with the point that we have is the minimum point. And the idea is exactly the same as in calculus 1, only projected to calculus 3. Two variables. So instead of looking at one derivative, we'll have two because there are two partial derivatives. And so you can guess what is so special about that point, or remember it from calculus 3, what is so special about this equilibrium minimum point in terms of the derivatives. They both zero. Both of them zero. Derivative. Remember, derivatives are the partial derivatives are the slopes. The slopes in these two particular directions, and calculus 1 applies. So in order for this to be minimum, it has to be minimum this way and that way too. Okay, which means that according to calculus one, you should have the derivatives, both the derivatives. Okay, so it's entirely comes from calculus one. It's not that complicated. Multidimensionality is the challenge. So this is one direction. So this is the x direction. Here, derivative have to be equal to 0. But if you go with y, it's the same story. Once again, derivative has got to be equal to 0 in that direction too. So this is my x and this is my y, and both of the partial derivatives must be zeros if this point to be a minimum. Okay, so set equal to 0, let's solve it. It's algebra is no more complicated than what we had, especially because the variables are now separated. Is no more complicated than calculus one. You're solving the problems that are very similar. Let's find minimum points, and what you do is set derivative equal to 0, solve it for x. And here the difference, because there are two partial derivatives, two unknowns, therefore more work to be done, but nonetheless the logic is the same. We find points x, y for which both the derivative equal to 0. It turns out there's only one such a point. So x must be gamma over delta, y must be alpha over beta. Okay, so these are indeed the equilibrium that we saw. The equilibrium from before. Right. So the something that we found in a manner that was entirely how we did find it. Remember, it's sign analysis. Well, we did pretty much. No, that's not. We remember how we did it. Now we did it. We used the right hand side. So in other words, we did not use G, right? We used the right hand side of the ODE. Right hand side of the ODE. Okay, so and then the effect was the same. So where derivatives are equal to 0, and then we found that special point. Okay, now we did the same. The answer is the same naturally, but we did it entirely different way. Okay, so the only critical point is in the quadrant x larger than 0, y larger than 0 of the local integral is the following. These x and y made of those two four parameters. Okay, so certainly you can look at it and see how the increasing of gamma move x in a particular direction. So that's certainly an exercise that you can carry out on your own. So as an exercise, so gamma goes up, delta goes up or down, and then what does it mean? In other words, so the equilibrium then moves, right? So remember what, for example, alpha was the natural rate of growth of the rabbits. Right, remember that? Alpha was in the very beginning the natural rate of growth of rabbits without foxes present. Okay, so if alpha were to increase, then y coordinate, then the whole thing goes up, or is it about the foxes? So if alpha goes up, y goes up, which doesn't seem to make a lot of sense. If alpha is going up, well, let me nonetheless take a quick look. So it's a while, so the meanings of the four parameters might be forgotten now. So let's refresh our memory. Refresh our memory. Okay, here it is. Okay, so here it is. So this is the basic model unconnected, unrelated to populations, and this is the alpha is indeed a rabbit's natural rate of growth. Okay, so once again the exponential growth. Okay, so increasing alpha increases the multiplying faster, but that does not change the x coordinate of the equilibrium. That turns out it brings the equilibrium for foxes in the up direction. Sure, I can give a good explanation to that, but certainly it's something to contemplate. So that's meaning of alpha. Meaning of beta is the interaction between rabbits and foxes, and so is gamma, and delta is the natural rate of decay or death of the fox. Okay, so those are the four numbers. They're combined together, so they're now to be combined, by the way, so alpha, beta, gamma, and delta, so in fact, so probably having a table would be a good idea like this. So, alpha, so x, uh, uh, x, y, x, x, y, x, y. So x on x, if you like, if you will, so it gives you alpha. So they interact with each other. And then the rabbits, that is, the fox is it's a gamma, delta. Okay, once again, foxes on foxes. So they're not killing each other, but nonetheless, they just don't have enough population growth to stop the decline. And then they interact with each other with a cross population from x's to y's. Then I have here, I have beta. Hold on a second, and gamma. Yeah. No, so alpha and gamma are the two. Yeah, gamma is the Fox's law. So alpha and gamma are the independent parameters, independent from the other one. And beta and gamma is actually what's happening in the forest. So they could be sitting in their holes and they reproduce. The rabbits will be reproducing and foxes will be dying out, really. And that's alpha and gamma. Describe that, how fast the growth or decline respectively. And then beta and gamma are beta and delta are the ones that describe how they interact with each other and how the rabbits are being eaten, right? Right. Okay, so let me scroll through this anyway. So these are the examples. So this is the fault analysis, remember, and that's how we establish this crossing a special value of x where the x is not changing, okay? And special value of y when y is also stuck. Okay, so and that turns out to be the equilibrium that we recovered in a different way. So it's the algebra that we just carried out. And so what else? Okay, so this is what we have. So the conclusion is based on the both analysis confirm the same thing. The only stationary constant solution is in that quadrant is that's the value. These four numbers combined together, and these are the equilibrium. By the way, if beta or delta is equal to 0, then everything breaks down. So in other words, this model breaks down as it's supposed to if there is no interaction between the two populations. So the conclusion that we have made about the repetitive nature of our solutions disappears. Okay, naturally, as one would expect, they would be separately from each other. So the only equilibrium point. So we know it's an equilibrium point, but it's a maximum point. And as you can see in 2 dimensions, just like should be the tip of your tongue, the function that has a 0 derivative, but not having a maximum minimum at that point is x cubed. Right? Remember calculus 1. So derivative, if it is a minimum, that it is derivative equal to 0, but converse is false. The derivative equal to 0 does not produce necessarily minimum or maximum. The example is x cubed to confirm that, but in dimension 3 it's even more complicated because there's an example. You might have a saddle point. So as you can see, the derivative, both of the partial derivatives of the 0, the tangent plane, by the way. So another thing from calculus 3, the tangent plane is horizontal. Okay, nonetheless, it's neither minimum nor maximum. And we've seen this. This is the remember the name of it. It is the hyperbolic parabola. So there is fortunately the second derivative, yes, just like in calculus 1. When you well, how do you know that the derivative is equal to 0 does not imply that's maximum minimum? So what do? We use the second derivative test, right? So x squared, just to refresh your memory, x squared is equal to x, z equal to 0, x is equal to 0. Maximum or the minimum, why minimum? We do not know that for a fact because of the of the problem that you just described, but you take the second derivative of 2x prime is equal to 2, which is positive, so then we conclude yes, minimum. So you see the logic? The second derivative is equal to 2, which proves that it's minimum. Why? How so? Second derivative is equal to 2. Why? How does that prove that we have a minimum?
Because it's concave.
Concave up. Positive second derivative concave up, and so it cannot be minimum, nor can it be this wiggle. This wiggle is also thrown out. Okay, so that's the second derivative. Yeah. Fortunately, there is a second derivative just for the functions of the variables, so it's more complicated. But so just pointed out that both of the derivatives are second derivatives are positive. So of itself, it actually is not enough to conclude that both derivatives are positive. Does not prove that it is actually minimum, but nonetheless. So there's an extra information, extra work to be done in this a matrix of made of not only second derivatives. That's not enough. You also throw in second mixed derivatives, second mixed derivatives. So dx dy. So dx squared, dy squared, and then you go dx dy, and you go dy dx. Okay, you bring them together in one formula. You bring them into this table, and then put the table of partial derivatives, which is called the Hessian. And then what do? You do the determinant. So that's the linear algebra that we'll need to learn. We'll need to learn a little bit about matrices, and we need to learn a little bit about the determinants in order to actually this quick note that I'm making here to put it on the foundation. Really, if you to do high dimensional calculus or differential equations, you cannot do them without linear algebra. So you have to do vectors, you have to do matrices, you have to do the determinants, and other related things. Okay, so determinant turns out to be, who knows what determinant is? The determinant of a matrix. Some of you do, some of you don't, so we'll review that. It's a big topic, obviously, but once again, you can't really do anything without. So it turns out the determinant is positive, and that is according to the theorem from calculus theory. It proves that it is indeed a minimum. That point that we are looking at is a minimum of that function g. So this is what it looks like if you want to walk curves. Okay, so everything. So we do not have a solution, but we do have very good understanding of what the solution curves look like. They go in circles. So it's a function. It's a function of the variables. It never goes down, by the way. So look at it. All the first derivatives are either all positive or all negative. The second derivatives, the concavity. Look at the concavity is entirely up. So the picture that Excel drew for us is true. Once we start cutting it like this, we'll produce a bunch of circular curves. And so we would pretty much have proven that the dynamics of this population, double population, is in fact cyclical. Okay, so all right, so but we don't have a solution. So what do we do? Let's do Euler. Let's do Euler method. And as an example, what do? We haven't done Euler's method in dimension 2, but it's the same story because you just look at your at your two derivatives separately, okay, and then you know which way to go. Okay, so that's roughly we did a little bit of that before, but we did remember when we did motion cannonball shooting forward, we had an x and y separately, and the computations were then also separate. But the idea is still the same. So at every moment of time, you know where you are, and then you know which way the arrow points. Make a step in that direction. You are in a new place. Once again, evaluate your function, your differential equation, find the arrow again, and you know where to go. It's the same story as in dimension 1. And if you do it, crude picture is on the right, more precise picture is on the left. As you can see, it is still not circular, but rather spiral. And it is spiraling. Look at it, spiraling out. Okay, so based on the right picture, you can actually tell why it is spiraling out and not in. Right, you see? we know that the correct answer is a circle, not a circle, but rather one curve that comes back. So this is wrong. We know that this is wrong. It's supposed to make a circle hit exactly at the spot where it started. It does not, but not only that, it comes out. So as you can see, getting more and more out. It is spiraling out, not in. So you see why it's not spiraling in.
Tangents always point outside.
Point out, right? So the tangent thing of the curve and will indicate that it's point out. Therefore, you look at what was going to happen if you follow the tangent. That's the conversation. Remember, we went on a tangent. The point is you never come back. Okay, so if you didn't go on a tangent, you would stick to that green curve and you wouldn't make a very nice circle. But once you off. You cannot come back to the same curve. Okay, so you are jumping. Look at it. It's actually visible here. You will start with the purple one, and then once you make a couple of tangential jumps, you're already on the blue one. And from blue one, you take a tangent, you're on orange one. From orange, you again in some kind of brown there, and on and on. So you're jumping from one curve to another curve to never come back. Okay, so that's the explanation of why we cannot have good things here, tangential behavior. Okay, so modeling is, once again, I didn't do a lot of it, because whenever we can solve the problem, we do, and so we did. But you can, the advantages, it doesn't look, and it is wrong, so we don't want to really do Euler's method here, because especially when it produces the correct result, we know it's incorrect, okay? So why do we do it in the first place? Because it's so easy to make a model. Let's make it just a little bit more complicated, just a little more sophisticated, be taking into account some other characteristics of things, such as this exercise right here. What if there is seasonal variation in terms of how the population grows, or how they are eating each other? And then what happens is the model breaks down. It cannot be handled algebraically in the same fashion anymore. So, and we're back to Euler's all the time. So then the best we can tell is that whatever we derive from Euler's method, and then will it be cyclical still? Well, that's unclear. That's entirely unclear whether or not they will be cyclical, even though the seasonal variability is periodic. But does that periodicity match the periodicity that we see here? And maybe not, in which case I have no idea what the correct answer is. Okay, any questions? Okay, I have a big diagram here to summarize what we have talked about in the spirit of so what calculus 2-3 and differential equations have in common here. Okay, so big diagram. So a system of ordinary differential equations are autonomous. So that's the difference is right here. I just pointed out predator-prey model with seasonal variations means that alpha, beta, gamma depend on p. Okay, so that's what makes it non-autonomous. But suppose it is autonomous. Okay, so then what is that we're producing? We're producing on the plane a vector field. Okay, which might look like those two pictures on the right. Okay, so and it might produce some kind of convergence of flow towards a point on the left, or some kind of circular motion, which we just saw. Okay, or a bunch of possibilities. So what we saw a solution and how we produce a solution is at the top we integrated the equation producing a function of two variables. Okay, so from the vector field somehow we found such a function of variables so that the solutions of our ODE travel along the level curves. Okay, so that's the possibility, and the then the no, that's not what happened. That's what could have happened, but it just didn't. Because our travel was along the curves, and the possibility that we have to keep in mind once you have a function of variables is actually the opposite, and that's the gradient. Everybody knows what the gradient is. Calculus 3. Well, those vectors are perpendicular to the level curves. Okay, so if you have surface, some kind of terrain given, and the tangent, not tangent, but rather level curve is drawn, as here, then you ask yourself which way the water will flow. And it will flow the fastest. So the opposite of those green arrows, and it will go down towards the bottom. And every time how it goes the fastest, meaning that it finds the shortest distance between two levels. Okay, how do you find the distance between two levels? What's the shortest one? And the answer is when it is perpendicular. Okay, so that's the fact of calculus 3, that it will be flowing in the perpendicular direction. Okay, so but nonetheless, this is the actually what did happen is, well, actually it did not happen on the left here. What it means to solve another differential equation is to produce a bunch of curves. Okay, parametric curves that cover the plane, hopefully on the xy plane. Okay, so that's what it needs to solve it. If you solve it, then you can just, if you're willing, you can abandon the time, which is here is actually hard to see, but actually these are pointer curves, so they are all labeled with when it happened. Okay, so if you were to drop that information, you will end up with nothing but curves like this. They fill the plane, and then you might ask yourself, are these roads possibly level curves of a certain function of the variables? And the answer is might, maybe, but doesn't have to be. So the examples that we had, we had exactly that. It is remember view from above on the function of the variables on the surface produces a bunch of curves that fill the plane as this like this. Okay, so it can happen, but it doesn't have to happen. Okay, so sometimes it comes from something more complicated than that. So the integral is of itself does not have to exist. So this is the ideal situation is at the bottom when you just somehow by magic solve the system of equations, and you end up with explicit equations for the solutions x of t, y of t, like that. In which case you can end up with the circular motion. Okay, so which is incidentally we ended up with circular motion when those arrows are arranged in that particular way. So all you see in calculus 3 primarily. So we're not much concerned with that here because this is what we're concerned with, and if we are not unable to do that, we usually just resort to Euler's method and what's coming up quantitative analysis. Okay, so we'll come back to that as necessary. Okay, so vectors. So let's review vectors on the plane. So nothing too complicated. And once again, the two things, if you remember physics, the vectors come. Two main motivations are their velocities and forces. We're not doing forces, so these are entirely about velocity. Okay, but the good idea to start it actually is slightly elsewhere, and that is with the locations, and then. Especially for modeling later on, this is very helpful when you're not changing continuously, but rather you're jumping location, and then you can say that what you were looking at, these vectors are not velocities, they're displacements. So if you have a sequence of locations, as you can see here, then you jump from one to the next, that bunch of vectors will be summarizing your motion. And so in addition to one way to look at it is a bunch of points, another way is a bunch of vectors. A vector which tells you where you are now, another vector you'll know where you are after that. Okay, so these are two sequences, and then the why do we care about this much is this on the right. We actually can do algebra. Okay, so that's why we want vectors. We want to be able to do algebra with them. And then this is the basic algebra that we want to do it. If we have had 4 increments, 4 displacements in a row, then what is the net displacement? You add these vectors together. How? That's how. Okay, just attach head to toe, and then look at the head to toe and the sum. So these 4 vectors, the beginning and the end. Once again, the net displacement will be the beginning of the first and the end of the plus. Okay, makes perfect sense, and that's why we want algebra. But generally, nothing. That's how we speak of vectors in any dimension. Is just 2 points, and then the vector is either PQ or QP. Okay, so and that's which one is I think the main question to ask So we're not gonna worry about it, but the point is that you can do it in any dimension that you like. We stick to dimensions. So, so PQ is not equal to QP. Once again, if you are in any doubt, think about displacements. And naturally, going from P to Q is not the same as going from Q to Q. So these are two different things. How much not different are they? Okay, it's the opposite displacement. Okay, which means what? Algebraic. How to express this idea that PQ is the opposite of QP? Negative sign, right? Negative sign, okay. So QP is equal to negative PQ, and that's the introduction into vectors. Even this could be one-dimensional totally, and it still makes sense to do algebra with vectors if you care which way you're moving. Okay, so these are not distances that elsewhere, especially if you study linear algebra, that comes up always distance, but distance does not depend on the direction. Okay, and here it does. And so if you were to study velocity, they are naturally, it matters which way we're moving, and so they are not interchangeable displacements and distance. Okay, so QP plus PQ, if I move this PQ to the right, I have QP plus PQ is equal to 0, which means that there is such a thing as 0. What is 0? What's the meaning of 0 in this context? It's still 2 points, but it's the same point. Right, so PP or QQ is that point in the vector that produces the 0. So as you can see, that's the logic that we can follow. Mixing up points and vectors. A point plus a vector gives you another point. That's how you move forward. So if you know I'm at P, I'm given vector PQ. I know I'm end up at Q. So that's the algebra that for uses both points and vectors very convenient way, and we don't have to worry about the things such as velocities yet. Because velocity, what is velocity? Displacement divided by time. Okay, so we're not dealing with that just yet. Okay, so that's PQ or P to Q, and then the vectors. There's a vector for each P. There's an infinitely many vectors originating from it. And then there are infinitely many vectors originating from Q, and we care about only one vector. This starts at P and ends up at Q. Okay, so that's the, if you were to describe motion, and once again, it's really not physics to speak of, it's algebra. So moving from point to point in an incremental fashion. So we are recording points, but if we were to kind of take a slightly more algebraic look at it, we also create vectors to describe the motion. So not only P and then Q, we say, well, PQ is our vector. That's how we have looked. Subtraction emerges right away. So that's how you can introduce a point, introduce a vector, you subtract 2 points. So point Q minus point C gives you vector P. P is the opposite direction. And so you can see how well it works out. If PQ is equal to Q minus P, then QP is equal to P minus Q, which is the opposite of PQ. So that's another way to arrive to the same conclusion. So QP is equal to negative PQ. So that's called the affine space. So the affine space Rn is actually a set of points. Okay, strings of n numbers. But then if you want to also bring a motion into this, then you bring also the vector. Okay, so it's a then there's a lot of stuff going on there. So just to quickly illustrate addition in dimension 1, it's literally addition of numbers. Okay, numbers, and then we do addition in dimension 2. Okay, I'll stop here. So let's see this.